Now we'll see the study of F block elements, that is lanthanoids and actinoids. Till now we were doing the D block elements. It is F block elements. The elements in which the differentiating electrons enter into n minus 2 F subshell, we can say that that is the F orbitals of the anti-penultimate shell are called inner transition elements. What I said, again I repeat, the elements in which the differentiating electrons enter into n minus 2 F subshell, that is the F orbitals of anti-penultimate shell are called inner transition elements, or it is also called as F block elements, or also it is F block consists of two series which is known as lanthanoid series and actinoid series. Lanthanoid starts from lanthanium, atomic number 57. Got it? Lanthanoid series is known as the first series of the rare earths, or the first inner transition series. This series is characterized by filling of 4f orbitals in the atoms and consists of 14 elements from cerium. Actually we say lanthanides because lanthanium we can say atomic number 57, but actually the electron does not enter into the F subshell in lanthanium. The electron enters into the F subshell from cerium itself, from cerium, that is atomic number 58. Alright, even if the series starts from lanthanium, mind it. And it goes to lutetium, that is atomic number 71. Got it? We can say that. It is in the periodic table, it resembles strongly in physical and chemical properties, and that is why they are called as lanthanoids, means strongly in physical and chemical properties to lanthanium. For that reason it is called as lanthanoid series. Similarly, the actinoid series is also referred to as the second series of the rare earth, or the second inner transition series. This series involves the filling of 5f orbitals in the atoms and consists of 14 elements from thorium. Here also what we see is that is it should be actinium, that is atomic number that is 89, but it starts from thorium, that is atomic number 90, because the electrons in the 5f orbitals enters from thorium itself, to lawrencium, atomic number 103. All inner transition elements are metals and occur very rarely in the Earth's crust. Therefore, they are collectively known as rare earths, or the rare earth elements. Alright, again I repeat, all inner transition, that is lanthanoids, actinoids, which you studied now, which you learnt it now, that is occur very rarely in the Earth's crust. Therefore, they are collectively known as rare earths, or the rare earth element. We can say that. Lanthanoids are also known as lanthanides or lanthophones. Lanthanones, we can say that, not lanthophones, I'm sorry, lanthanones. Alright, now you can see these things are written there on the screen. We can say that it is lanthanides or D block elements included in the lanthanoid series, closely resembles lanthanoids, and actinoids also actinoid series. We can say that that is they are complicated, partly because they show a wide range of oxidation state, and partly because they are radioactive. Alright. So now we will before moving to the next, we will see, that is occurrence. Lanthanoids are regarded as rare earths, yet they are not much rare. They are widely distributed in nature in minute quantities. They are found in nature. We say rare earth, but it's not so rare. It is widely distributed in the nature, we can say that. Promethium is an unstable radioactive element and does not occur in the Earth's crust. Thallium, we can say that, not thallium. Thallium is also much less abundant in Earth's crust. Alright. The electronic configuration of lanthanides are known with certainty, not known with certainty, the electronic configuration. This is because the electronic spectra of lanthanoid atoms and ions are so complicated that it's very difficult to ascertain their correct configuration. Just now, which I was saying you, that is on the screen, you can see that the chemistry of actinoids is much more complicated. You will see, this is lanthanoids I'm talking to you. When I'll say about actinoids, you will see it is much more complicated than lanthanoids. We are saying lanthanoids are complicated. It has got a very difficult to ascertain the correct configuration. Alright, it's very difficult to ascertain the correct configuration, but actinoids are still more complicated than lanthanoids. Still more. The predicted and observed electronic configuration of lanthanoid atoms, and the observed configuration of there is M2+, M3+, and M4+ ions. Alright, the predicted and observed electronic configuration of lanthanum, that is lanthanoid atoms, and the observed configuration of their ions are M2 plus, M3 plus, and M4 plus. That means they exist in M2 plus, M3 plus, and M4 plus ions, so to say. The electronic configuration of lanthanum La57 is 1s2, 2s2, it will go up to 6s2, 5d1, 6s2. In lanthanum, the differentiating electron, I am just explaining you what we studied by taking the example of lanthanum. Alright, so listen carefully. So in lanthanum, the differentiating electron enters into 5d subshell. 5d1 I said, 5d1, 6s2. Because the energy of the 5d subshell is lower than that of the 4s subshell. 5d, 5 plus spd, 5 plus 2, that's 7. 4f, that is 4 spdf, spdf, that is 4 plus, that is 7. Alright, so 5d subshell is having lower energy than that of 4f subshell. After lanthanium, the next element is cerium, which is the first member of the lanthanoid series. Here the 4f subshell has lower energy. Alright, here the 4f subshell has lower energy. In lanthanium, the 5d subshell has lower energy. So the differentiating electron enters into the 5d subshell. But in cerium, the 4f subshell has lower energy and the differentiating electron enters into the 4f subshell. It is not certain whether Ce contains a 5d electron or not. It is supposed that at this stage 5d orbitals possess higher energy than that of 4f orbitals. Alright. For that particular reason, the 5d orbitals in case of cerium possess higher energy than that of 4f orbitals. So in case of cerium, the differentiating electron enters into the 4f subshell because it is having lower energy. While in lanthanium, 5d orbitals have got the lower energy. Understood? So it is quite complicated, this particular things are. Now, the most common oxidation state I said you already, it is plus 2, plus 3, plus 4. But out of that, that is the lanthanoids also exist in plus 3 state, which is more stable than plus 2 and plus 4 in aqueous solution. Got it? In aqueous solution, plus 3 state is more stable than plus 2 and plus 4. The plus 2 oxidation state, this state is not much common in lanthanoids. We can say that, not much common. Got it? Their dye-positive ions exist in solution and a strong reducing agent. They are. Got it? They are strong reducing agent. The plus 3 oxidation state, this is the most common oxidation state of lanthanoids. Lanthanoids form compounds with almost all ions in this state. All anions rather I should say in this particular state. That is, they form hydroxides, carbonates, sulfates, oxalates, nitrates, etc. We can say that. The salt decompose on heating, first forming basic salt and finally changing into their oxides. We can say that. The anhydrous salt simply melt without decomposing on being heated, so to say. The plus 4 oxidation state, which you can see, this state is also not very common. We can say it is not very common, the plus 4 oxidation state. Alright. Dysprosium is found to exist in plus 4 state. We can say that. Dysprosium, that is dy, we can say that. It is supposed to be existing in the plus 4 oxidation state. Clear? Otherwise, the plus 3 state of all lanthanoids are stable in solution, but only few plus 2 and plus 4 states are stable in solution. If you see the magnetic properties, then most of the ions of these elements in plus 3 states are paramagnetic in nature and possess a definite value of magnetic moment. La3 plus and Lu3 plus possess a zero value of magnetic moment and do not show paramagnetic character. Note it. La3 plus and Lu3 plus ion, lanthanium and lutetium, the first one and the last one, possess zero magnetic value of magnetic moment and do not show paramagnetic character because it is fully filled. For that particular reason, you can say that. Clear? So it is zero value of magnetic moment, you can see. Fine. So paramagnetism is actually contributed with the spin of the electron as well as its orbital motion. Alright, due to which it possesses the paramagnetism. Therefore, in case of lanthanoids ion, the paramagnetism is due to the both factors, that is electron spin and the orbital motion. Alright, and the magnetic moment of the electron spin is only given by root over of 4s into s plus 1, where s is the total spin quantum number. Whereas the magnetic moment due to orbital motion is given by, that is mu L is equal to, mu is your magnetic moment, isn't it? Root over of L into L plus 1, capital L, where capital L is the resultant orbital quantum number. Again I repeat, the magnetic moment due to spin is given by mu s is equal to root over of 4s root over of 4s and s plus 1, whole everything inside the root over of 4s and s plus 1 within bracket, whereas the magnetic moment due to orbital motion is given by mu L is equal to root over of L into L plus 1 within bracket, we can say that. So L is the resultant orbital magnetic resultant orbital quantum number, we can say that. Clear? And the sum of mu s and mu L is represented by mu j, and mu j is equal to g within square g, then you start a square root, within square root you write j into j plus 1, where j is equal to L plus s, where g is the small g is the termed as a splitting factor. Got it? G is termed as the splitting factor, where J represents, already I said you, J is nothing but the result represents the resultant quantum number, where J is equal to L plus S. Got it? J represents the resultant quantum number, which is J is equal to L plus S. Fine. Now the color of the ions, if you see, then you will find that except few exceptions, the tripositive ions of lanthanides are colored. They are colored. Few exceptions means lanthanum, cerium, then that is your GD3 plus, got it, and as well as U3 plus, got it. Now that is GD is nothing but gadolinium, and EU is nothing but europium. Leaving behind this, that is europium is nearly colorless, we can say that, whereas GD3 plus, that is your gadolinium is, and cerium and lanthanum, they are colorless. Otherwise all are colored, we can say that. All are colored ions, we can say that. Similarly your lutetium is colorless. Similarly your ytterbium is colorless, we can say that. YB, that is ytterbium, that is YTTERBIUM, ytterbium, that is YB, it is colorless, we can say that. And they are all colorless ions, we can say. Usually the color of the ion, you know that, you have read it already. It depends upon the number of unpaired electrons present in it, and it should deepen with the increase in number of unpaired electrons. Got it? Usually the color of an ion depends upon the number of unpaired electrons present in it, and it should deepen with the increase in the number of unpaired electrons. The 4f orbitals are quite deep inside the atom and are well shielded from environment, we can say that. The color of an ion results from the absorption of certain wavelength in visible region. This absorption depends upon the energy needed for excitation of electron from a lower level to higher level. Since in lanthanoids the unpaired electrons are present in F subshell, the absorption of visible radiation causes FF transition. Just you have studied in CFT DD transition, here it takes place as FF transitions. Got it? The FF transitions is taking place, and due to which the energy required for the various FF transition is different in different cases. And as the available F orbitals are different from one another, this is why lanthanoids shows various anomalies, got it, as far as the colors are being concerned, we can say that. Now this is just for some of the properties I was talking to you. Now you can see there is a regular decrease of contraction in the atomic and ionic radii of lanthanoids with increasing atomic number. Got it? This is called as lanthanoid contraction, we can say that. It has been observed that on moving from cerium to lutetium, the size of the atoms and the ions decrease regularly. This decrease in size is more regular in case of tripositive ions, we can say that. Got it? That is, when one moves from cerium to lutetium, the nuclear charge increases. Listen carefully. The nuclear charge increases with atomic number, and the differentiating electron is added in the inner 4f orbital. In the inner 4f orbital, the shielding of one 4f electron by another from the increasing nuclear charge is very much imperfect due to the peculiar shapes of 4f orbitals. Therefore, with the increase in atomic number, the effective nuclear charge experienced by each 4f electron increases. This causes a slight reduction in the size. Got it? See, definitely, when the electrons enter into the inner shell, what will happen is that the size is going to decrease. Due to the increase in nuclear charge, the size is going to decrease. Got it? Slightly, it is going to decrease. With the increase in atomic number, the effective nuclear charge experienced by each 4f electron increases. This causes a slight reduction in the size with the addition of each electron in the 4f subshell. Thus, with the addition of each electron in 4f subshell, there is steady increase in the effective nuclear charge, resulting in the steady contraction in the size. As the effective nuclear charge is going on increasing, got it? With the increase in atomic number, there is also steady decrease in the size, the contraction in the size, because as the nuclear charge is increasing, you know that atomic size decreases. The successive contractions get accumulated, and the total effect of all the lanthanoids is termed as lanthanoid contraction. This is known as. So hence I said, you can see it on the screen, the regular decrease in the atomic and ionic radii of lanthanoids and actinoids. We can say that lanthanoids and actinoids with increasing atomic number is known as lanthanoid contraction. Alright, it's known as lanthanoids contraction, we can say that. And the causes, I have said you can see it on the screen, I have written it on the screen, the causes I have told you. Alright, you can go through the causes. Now, that is the imperfect shielding is unable to counterbalance the effect of the increasing nuclear charge, hence the net result is a contraction in the size, though the decrease is very small. It's very small, the decrease is very small. It's not a large decrease in contraction is taking place. Thus in lanthanoids the valence shell remains unchanged. Got it? Listen carefully. Thus in lanthanoids the valence shell remains unchanged, yet the size of the atoms and the ions decreases with increase in atomic number due to lanthanoids, because electrons is entering into the innermost subshell, that is a 4f electron. So there the nuclear charge is increasing, there the atomic size is decreasing, but the outermost valence shell remains unchanged. Got it? So hence I said, thus in lanthanoids the valence shell remains unchanged, yet the size of the atoms and ions decrease with increasing atomic number due to lanthanoid contraction. Got it? Now the cause of lanthanoid contraction is that is generally the atomic and ionic radii increase in a group with increasing atomic number. Got it? That is, it increases with increasing atomic number. The next cause is that due to lanthanoid contraction, you can see there is consequences, you can see it there. Yes, I am talking about the consequences. That is the change in ionic radii, the size of the ions and lanthanoids is very small. The chemical properties are being similar, that is due to lanthanoid contraction the basic strength of oxides and hydroxides of lanthanoid decrease with increasing atomic number. Alright, the basic strength of oxides and hydroxides of lanthanoids decrease with increase in atomic number. That is LaOH whole thrice is most basic, while LuOH whole thrice is least basic in nature. Least basic, we can say that. Therefore, with the increase in atomic number, the polarizing power of lanthanoids cations increases. This results in a regular decrease in the ionic character of oxides and hydroxides, and they become less and less basic. Now next is that the density, if you see, that is a reduction in the size of the atom due to lanthanoid contraction increases the densities of all the elements placed after lanthanoids abnormally. Alright, a reduction in the size of the atom due to lanthanoid contraction increases the density. Definitely when due to contraction the volume will decrease, so density is going to increase. Got it? Of all the elements placed after lanthanoids abnormally, we can say that. The phenomena of lanthanoid contraction also affects the value of ionization potential. Ionization potential of all the elements of the third transition series from tungsten onwards. Got it? The phenomena of lanthanoid contraction also affects the value of ionization potential of the elements of the third transition series from tungsten onwards. In the absence of lanthanoid contraction, these values should have been much lower and should have decreased regularly on descending down the group. Now, that is Yttrium. Yttrium is a member of the group 3. You know that Yttrium denoted by Yt. Already I said you there is Yttrium. So now you know that Yttrium, that is it is having that is Yt as a symbol. Okay, so the group 3 and belongs to D block of the periodic table. These elements quite unexpectedly occurs along with the heavy lanthanoids. See, listen carefully. It is D block. Now what I am teaching you now, it is F block. But Yttrium is a member of the group 3. Alright, and belongs to D block of the periodic table. But this element quite unexpectedly occurs along with the heavy lanthanoids. It is occurring with the heavy lanthanoids. This is being occurring. That is Yttrium. We can say that. Clear? that is YT, we can say that. Clear? So it is very, very important to note this particular point, we can say. Clear? So lanthanoids belong to a block and should occur independently. This unusual occurrence is a consequence of lanthanoid contraction, we can say that. Now, as compared to D block transition elements, lanthanoids form only few complex and less readily. Got it? As compared to D block transition elements, lanthanoids forms only few complexes and less readily. We can say that, less readily. Got it? So you can see it in the size here. You can see it on the screen there. The similarity in size of the atoms of the elements belonging to the same group of second and third transition series is evidently due to the effect of lanthanoids contraction. As the size of lanthanoids ion decrease from La3 plus to Lu3 plus, the covalent character of hydroxides increases. Thus, just now I discussed with you, LaOH whole thrice is most basic, whereas LuOH whole thrice is least basic in nature. Now, that is a formation of the alloys. Lanthanoids are highly dense metals and possess high melting points. They readily form alloys with other metals, especially with iron. Especially with iron, we can say that. Then reactivity of the lanthanoids, if you see, due to similar outer electronic configuration and their existence in mainly +3 oxidation state, lanthanoid shows very similar chemical properties. Very similar chemical properties. The lanthanoids are highly electropositive and highly reactive elements. Lanthanoids are highly electropositive and highly reactive elements. Lanthanoids tarnish readily on exposure to air, resulting in the fading of the silvery white luster. They burn in air to form their respective oxides. They react with hydrogen to form non-stoichiometric hydrides. They react with nitrogen and warming to form nitrides. They react with nonmetals to form corresponding compounds. They dissolve readily in warm water to liberate hydrogen. So these are the reactivity of lanthanides I told you. That is the lanthanides which are highly electropositive and highly reactive elements. How we can come to know from this that they react with nonmetals, they dissolve readily in warm water, they react with nitrogen to form nitrides, we can say that. They react with hydrogen to form non-stoichiometric hydrides, they burn in air to form respective oxides in this way. Got it? So that is characteristics of lanthanides. We can see it on the screen also, I have written there. Got it? It forms FF transition. Clear? The first members of the series are quite reactive, almost like calcium. However, with increasing atomic number, the behavior becomes similar to that of aluminium. Got it? This is of there is your lanthanoids. Now, coming to the actinoids, we can say that. So, the first 4 elements of the series, that is actinium, thorium, protactinium, and uranium, occur in the Earth's crust. The remaining elements of the series do not occur in nature and have been prepared artificially by nuclear bombardment. Note it, the remaining elements of the actinide series are prepared artificially by nuclear bombardment. The actinoids beyond uranium are referred to as, for that reason, transuranic elements, because they have properties similar to that of uranium. As in case of lanthanoids, the electronic configuration of actinides are also uncertain. This is because of the energies of the 5f and 6d subshells are almost equal, and it is difficult to ascertain whether the differentiating electron enters into 5f subshell or 6d subshell. It is very difficult to ascertain. Got it? So it is very complicated. I told you earlier only. The most common oxidation state exhibited by actinoids is +3. Besides the oxidation state of +3, actinides also exhibit oxidation state of +2, +4, +6, 5, +6 and +7. Got it? Actinoids starting from actinium and it goes to lawrencium, already I said you. Actinium, that is atomic number 89, but the first electron of the 5f subshell enters from thorium itself and it goes to lawrencium, Lr, we can say that. The ionic radii of actinoids decrease regularly across the series. The phenomena is very much similar to lanthanoid and is also termed as actinoid. Just like lanthanoid contraction, we are also having the actinoid contraction. The ionic radii of actinoids also decreases regularly across the series. As the nuclear charge increases, atomic number increases, so the differentiating electron enters into the 5f subshell. Alright, so due to this reason, there is a decrease in the what you can say actinoid and this particular contraction is called as actinoid contraction, and this is due to the poor shielding of the nuclear charge by 5f electrons. Now most of the actinoid ions are colored. They are being colored. Most of the actinoid ions are colored. The ions having 5f0, 5f1, 5f7 configuration are colorless. Note it. The ions having 5f0, 5f1, 5f7 are configuration are colorless, while those having 5f2, 5f3, 5f4, 5f5 and 5f6 configuration are usually colored. I've said you just in lanthanoids only that as the number of unpaired electrons is increasing, the color getting deepens and deepens. We can say that. Clear. Magnetic properties. Most of the actinoid cations exhibit paramagnetic behavior. Paramagnetic behavior. In general, the tripositive and the tetrapositive cations are paramagnetic in nature. Actinoids are silvery white metals having high melting and boiling points, except thorium and americium. They possess high densities and all are radioactive in nature. So actinoids are highly electropositive elements, therefore they are quite reactive and combine with hydrogen, oxygen and halogens and acids to form corresponding compounds. We can say that corresponding compounds. Now here is you can see on the screen the comparison of lanthanoids and actinoids is given there. You can go through it. Both are electropositive and very reactive. Both with oxygen state of +3. Both are magnetic and spectral properties. Both exhibit. Actinoids exhibit actinoid contraction, while lanthanoid shows lanthanoid contractions. We can say that. Clear. So this is all about your lanthanoids and actinoids. Thank you.